everybody. Welcome back. Mr. Hartman here, once again talking about science, 2021, astronomy, and today we're going to talk about gravitation from Galileo and Sir Isaac Newton. So let's start with Galileo. He was born in 1564. He was an Italian astronomer and physicist, and he developed a heavy interest in the motion of falling objects. He discovered that objects in free fall moved too quickly for him to accurately measure just with, basically whatever tools he had in his eye. And so what he did instead is record how long it took metal balls to roll down an incline, creating a water clock of his own invention to measure time, which is awesome. And at this point, he discovers that falling objects don't move at a constant speed as they continue to roll down. The metal balls continue to roll down the incline. They speed up as they go. And then he found that this rate of acceleration was the same for every object, regardless of mass. And so that really starts the clock ticking on, figuring out gravity and all that stuff and how that works. In terms of astronomical stuff, Galileo becomes the first person to make astronomical observations using a telescope. He does this in 1609, and he's able to see the mountains, craters, and dark areas of the moon. He's also able to view sunspots and their movements. I think he actually names a lot of these dark areas, if I recall. I forget. We'll get there when we get there. We're talking about a lot about the moon, but we won't stop talking about the sun. Galileo also then discovered the 4 largest moons of Jupiter, which is very, very important because what we see is we have another celestial body that has other objects orbiting it, which essentially destroys the geocentric model of the universe that the Catholic Church had subscribed to at this point. And for those who don't know why the Roman Catholic Church really heavily leaned on the geocentric model of the universe, it's because if the world doesn't revolve around the Earth, right? If the universe doesn't revolve around the Earth, then the idea of us kind of being God's chosen people kind of goes out the window, right? It really opens up the door to a lot of different possibilities that kind of conflict with the idea of Jesus as kind of the savior of man and God as the creator of our world and stuff like that. So that's why they're not too big of a fan of this idea. But again, as I said, Galileo's discovery of the 4 largest moons of Jupiter confirmed that the Earth is not the center of all planetary motion and helped support the Copernican theory. He also observed that Venus regularly changes size and shape, which according to the Ptolemaic system, if you recall, the Ptolemaic system is the geocentric model where everything revolves around the Earth. This shouldn't happen according to the geocentric model, even with the idea of deference, right? Even with the idea of them moving in their orbit, right? So according to the Ptolemaic system, Venus and Mercury should only ever appear in the crescent phase. They should never appear in any other type of phase. The crescent phase would be, obviously the small crescent, but that happens because of the lights reflecting from the sun. However, the Copernican system, if they apply that to the Galileo's observations, that makes it a much simpler explanation in that Venus and Mercury exhibited phases as they reflected sunlight to Earth from different places in their orbit around the sun, right? Specifically Venus and Mercury because they're the 2 inferior planets. Planets are closer to the sun than Earth. So the superior planets are going to be Mars, Jupiter, Saturn, Uranus, and Neptune. The Roman Catholic Church banned books that supported the Copernican theory in 1616, so a few years after Galileo makes his discoveries. However, Galileo has continued to do astronomical research as long as he does not hold, teach, or defend any doctrines that are contrary to the views of the Church. And then 16 years later, he holds, teaches, and defends doctrines contrary to the views of the Church when he publishes Dialogue concerning the 2 chief world systems, which supports the Copernican system despite these warnings from the Church to not do this. And then the next year, 1633, Galileo is forced to recant his astronomical findings by the Inquisition, not the Spanish Inquisition, just the larger Inquisition. The Inquisition was not just a Spanish thing. It just happens to be that the Spanish one is much more well-known and dangerous. And at this point, Galileo is condemned to house arrest by the Inquisition. It is not until 1992 that the Catholic Church vindicates Galileo and overturns this verdict against him. Took them long enough, but they did it eventually, right? So that's Galileo, and then now let's talk about the laws of Sir Isaac Newton. So Isaac Newton revolutionizes physics and astronomy, and of course mathematics. And the way he did this is by explaining why the planets move the way they do. He answered the reason that Kepler brought up, right? Kepler again created the empirical observations of the different movements of the planets. Newton is the one to properly explain why that is. Newton's from England. He's a physicist and mathematician. And in 1687, he publishes one of the most important books ever, The Mathematical Principles of Natural Philosophy, also known as the Principia or Principia. And he proposed the 3 laws of motion and the law of universal gravitation in this book. Obviously, the 3 laws of motion: an object at rest or in motion will maintain that motion unless acted upon by an outside force. We also have the second one, which is an object's acceleration is directly proportional to the net force acting on it and inversely proportional to the object's mass. And then thirdly, to every action, there's an equal and opposite reaction. After creating these 3 laws, setting these 3 laws of motion in play, he then turned his attention to falling objects, and he reasoned that there must be a constant force causing the change in speed. But Newton, so this is the same idea that Galileo came up with. The difference for Newton is that he recognizes that this same force that keeps causing this constant change in speed of objects falling is also the exact same energy, the same force that is keeping the planets orbiting around the sun. Of course, that's gravity, right? And Newton is able to calculate the strength of this force between the Earth and the Moon that is required to keep the Moon in orbit. And to do so, he invented differential calculus. So calculus was created for astronomy. So that's cool. And Newton's law of universal gravitation is that the force between 2 objects is directly proportional to the product of their masses. And then the force between 2 objects is also inversely proportional to the square of the distance between them. And here mathematically, we have the equation F equals gm1 m2. Those are supposed to be subscripts, I think. Yes, I believe they're supposed to be subscripts. Let me see if I can change this on the fly. Script, subscript. Okay, I can. It's just going to be a pain. Cool. There we go. And then we'll do that. Sorry about this, folks. You're seeing the meat get made, as it were. Come on. There we go. So M1 and M2 are the masses of the objects, right? So that's mass. So those are just the names for the mass of the different objects, because we have to be talking about 2 objects. R is their distance, how far they are separated. It's measured from the center of the object. And then G is the gravitational constant, which I don't think they ever give a proper example of what exactly the gravitational constant is. But what this is called is an inverse square law. So the magnitude of the attraction between 2 objects decreases in proportion to the square of the distance between them. So as an example, the distance separating 2 objects is doubled. The force between them goes down to 1/4 of its original strength, right? If it's tripled, it goes down to 1/9 of its original strength, right? So it is very much affected by the distance between the objects, a lot, right? Magnitudinally. The gravitational force between any 2 objects acts in equal magnitude on both objects. So the sun's gravitational attraction on Earth is equal in magnitude to the Earth's gravitational attraction on the sun, right? That's because the distance that they're at, right? The distance that they're at, right, creates this equality, right? Finally, all sciences are collaborative and interactive, requiring the effort of many people over prolonged periods on similar, more complicated problems. And Newton himself said, "If I've seen farther than others, it's because I've stood on the shoulders of giants." Those giants he's talking about are Galileo, Copernicus, Brahe, Kepler, and probably many others. However, Newton's model doesn't create a complete description of the role gravity plays in our universe. And we see later physicists will stand on Newton's shoulders to refine our understanding of gravitation. And that's it for this video. Do my best to cover Newton and Galileo, two again, monsters, two giants in our world. In the next section, we'll cover electromagnetic radiation, And then after that, we'll cover the electromagnetic spectrum. Getting into the weeds on this a little bit. This is where I think it can get a little tricky. Hopefully I can do my best to explain it. But until that one, thank you guys so much for watching, and I will see you